Hi guys, welcome. We are the Webee machine monitoring team, Param, SQ, and James. That's it. Alright, so this is our team. Starting off with Shikwan. He's a master's student in industrial engineering. And then there's me, Param Patel. I'm a freshman in computer science. And James, a master's student in business analytics. Okay, so our project. Our team was tasked by Webee to analyze sensor data, and this data is coming from rotating machines in the industrial setting, so things with motors inside them. And in order to analyze this data, we were given the task to use prescriptive maintenance, which is basically something that analyzes equipment data to reduce operational risks. So we can predict when something might break or a malfunction might be approaching. And the way we could do this is using unsupervised time series anomaly detection. So the unsupervised means that we don't have any ground truth basis as to when the machine might or might not be broken within our data. And then we use time series anomaly detection, which is just basically anomaly detection bounded by a certain time, so hours, days, weeks. And we use that methodology to reach our goal. So Webee is a company that uses IoT sensors that are attached to these motors within the industry. So it'll record data, things like acceleration, velocity, temperature, and current of the machine, and it'll upload it to the cloud, and that's where that data is stored. Our dataset does have a few limitations and conditions. The limitations start off with the datasets don't have paired variables, so if you have acceleration, you may or may not have that respective acceleration's velocity data or current data, and vice versa. Additionally, there are no specifics as to when the machine is on or off, so we have data when it's off, but we don't know if it's specifically on or off. Furthermore, we also have data collected by the IoT sensors that we don't know if it was suitable for vibration analysis, and that was one of our first ideas looking at the data set, if we could conduct analysis on vibration. And in terms of operating conditions, our team focused on a group of data sets that were all next to each other within the facility. So if there were multiple machines next to each other, these data sets would record data, but sometimes the noise from one machine could affect the other machine's data. So our overall game plan or our pipeline workflow was to use what we have detailed in this chart over here. It does look pretty big and scary, but we'll explain it in the slides following. But overall, we just plan on using pre-processed data in order to get towards time series data using moving averages, so the respective average of data over time. And then we split those into subsets and run different models in order to get a score based on results, which is the end product, whether the machine will or will not fail.
So our first step was to pre-process the data in order to understand and to clean the data. We first dropped the irrelevant columns and merged the acceleration and velocity data with the same timestamps. So not all data could be paired, so this resulted in certain NA values. We then had to impute in order to replace the missing values in temperature and velocity. Due to the high correlation between velocity and acceleration, we used a polynomial fit between the two variables to estimate the missing velocity values. We then used interpolation for the missing values for temperature values. And then the imputation process accounted for about 30% of the data set. So as mentioned, the data consists of both cases when the machine is on and when it is off. Hence, we needed to find a way to split the data set between both of these cases. Since the data follows a bimodal distribution, we used GMM to determine a value for the splitting point. As shown in the resulting histograms, we were actually able to split the data between when the machine is on and off using GMM. The next step we did was to try to capture more information from the data set. To capture more information in the data in the time domain, we calculated the moving averages. This helped to reveal certain trends within the data. Next, we also used root mean square in order to aggregate the data from the x, y, and z coordinates that was captured by the sensors.
Now that we had our prepared data set, we were ready to start modeling our data through several models to see if we could detect anomalies. A couple of the models that we used were sport vector machines, QSUM, and Mahalanobis distance. All these we would run the data through and use each one to try to detect anomalies within the data. With the result of each of our statistical models, we were able to aggregate them by day and assign a weighted score to each day based on the number of models that detected an anomaly. And each of those scores was then ranked relative to past data, so that items that were within 1 standard deviation of the score were a low risk for an anomaly, but days where we had more than 3 standard deviations above mean, then those we ranked as a high risk for an anomaly. Going forward, using the output from our models, we are going to work with Webee to integrate this with their current software to make it available to their clients, and see some online testing and validation through real-world usage. Next steps will be probably to improve the model using labeled data to enable us to commit some prescriptive maintenance. Throughout this project, we've had a lot of help from several outside resources, including our TA, Luke, our Webee team members, Devor, Lucas, and Dario, and then countless resources online, including several of the main links listed here on this slide. Thank you all for your time, and we've really enjoyed working on this project.